So in this video, we are gonna continue the discussion on this first lecture, product, process, and schedule design. And last time we discussed up to this slide in which we were calculating the production requirements for a serial process with 3 operations. And we show that given an expected output in terms of the number of goods units to be produced, in this case 97,000, and knowing the percentage of parts that were expected to be defects for each one of the stations. In this case, we have 3 stations. Knowing the expected output and knowing that expected defect rate for each one of the stations, we computed the required input, in this case, input 1, in terms of how many units we needed to start with in order to achieve that desired output for our process. So in this case, our desired output was 97,000 units. And by computing the inputs for each one of the stations at the end, input for the initial part of the process was equal to 105,219 units. So this next example is going to follow the same ideas, but the main difference between this one and the previous example is now we have rework. And what that means is we are not discarding all the units that are defects. So for instance, in this first station, those units that are defects are going to another process or another station that is called station number 2, and for some rework, meaning that some of those parts that are processed in that station will go back to the process and will be usable in terms of being in good shape to complete the process. So for this problem, what I'm going to do is I'm going to solve, or basically you can see the equations here. So I'm going to develop an expression that is going to allow you to compute this I1. Okay, so that's the goal. So as you can see in this example, we have no numbers, so I'm just going to develop the equation based on the information that we know for this. So so we know we have a ratio of defects for each one of the stations, including that station that is rework. And we can use a variable to determine or to model what it will be the output and the inputs for each one of the stations. Okay, so as I mentioned, the calculation of I1 is our goal for this problem, and it's going to be based on the required output 3. O3. Okay, so we can start with that. We know that there's a requirement, that's the output, and we want to know what is I1 based on that requirement at the end of the process. So I'm going to state some of what we know. So we know that that output of 1 is going to be equal to the input of that station times 1 minus the rate of defects, right? And we know that the input of 2 is going to be whatever comes down as a defect times the percentage of the defects for that first station. So I2 is going to be equal to the input that we are going to receive in station 1 times the effects. And we know that if we sum all1 plus I2, the total should be equal to I1. Okay. So we know D1, we know I1, we know O1, we know I2. So the next thing that we want to use is the definition of O2, and we know that's going to be equal to the output of 2 is going to be equal to the input of 2 times 1 minus the defects that we are going to see in that station. Okay. So knowing all that information, now we have the information for O2, we have the information about O1. So we know that at this point, this node is going to receive both O1 and O2. So the input of 3 is going to be the summation of those two. Okay, so I3 is going to be equal to O1 plus O2. And we have already defined the expressions for O1 and O2. So we have O1 here, and we have O2 here, which means that we can use that information or we can substitute that information into our equation. So O1 equals I1 times 1 minus D1 plus I2 times 1 minus D2, which is these two expressions. I'm just substituting those two expressions into I3. So what I'm trying to do here is I want to generate an expression that will limit the number of unknowns, right? So at the end, I will have an expression that I can substitute the information that is known, and we will be able to compute the value for I1. Okay, so the information that we know is the defect rate, and we also know the output 3. That's the information that we have. So we have to generate an expression that will be based or will be stated in terms of the D's and in terms of O3. So, okay. So we also have some information about I2, right? We know this expression. So I'm going to substitute I2 into this equation. So I1, 1 minus D1 plus one minus D2 times the substitution, which is this one, I1, D1. And if I do some math here, I can find that I1 is a common parameter for both expressions, so I can take it out, and then I can do this plus d1 times 1 minus d2. So right now, this is my unknown. I know this parameter, I know this parameter, and I know this parameter. Those defective rates are going to be given. So the only unknown, I want to solve for I1. That's my goal. I want to find the value of I1. But the only unknown as right now will be that I3. I don't know what that value is. So what I'm gonna do now, I'm going to solve for I1. So I want to make I1 because that's my goal. I want to compute I1. So I1 is going to be equal to, so I'm substituting for I1. It's going to be equal to I3 divided by this expression, 1 minus D1 plus D1 times 1 minus D2. We can elaborate an expression for I3. We know that I3 is going to be equal to O3 divided by 1 minus D3. And then we can substitute I3 into here. So at the end, I1 is going to be equal to O3 divided by 1 minus D3 times 1 minus D1 plus D1 times 1 minus D2. And that is the final expression. So using this expression for this problem, I can find the value of I1 by substituting the information that I know. In order to solve this problem, I will know what will be the required output for my process, and I will know what are the defective rates, D1, D2, and D3. So with this expression that we just developed, given those values, I can compute what will be this, the required input for my process. Okay, so next we have the next topic, which is facilities design. And in this topic, we are going to see how the product process and schedule designs are used to guide the decisions for the design of a facility. So once the product process and schedule design decisions have been made, the facilities planner needs to organize the information and generate and evaluate the layout, handling of the product, the storage, and the unit load design alternatives. The 7 management and planning tools that we are going to discuss next have gained acceptance as a methodology for improving planning and implementation efforts. So the first diagram is called the Affinity Diagram. And the Affinity Diagram is used to gather variable data, such as ideas and issues, and use that information and organize it into groups. So for example, in figure 13, I have an affinity diagram example for a problem that is looking at reducing the manufacturing lead time. So, as the first thing we are trying to do is to gather information. This is verbal information, and we are grouping that information into the larger issues. So in this case, those issues are facilities design, the equipment issues, the quality, the setup time, and the scheduling. And how we got to that point? Well, we started interviewing people that are associated to the problem, and this is the information that we started gathering. We started gathering this type of information. So in terms of, for example, facilities design, maybe there's a need for forming product families. Like, for example, if you think about cell phones, Samsung, for instance, they have multiple different type of phones, but some of them are more, let's say, some of them are focusing on being less expensive. So you have multiple units or multiple models that are similar. That could be named as a family. And then they have their key products, such as the Galaxy and the Galaxy Note. So those by themselves can be categorized as a separate group, as a separate family. So the process of producing those cell phones are different. So if we can separate them as families, then, for example, things such as setups can be reduced. We can produce this family first, and then we can do the setup and produce the next family. So maybe in this example that's not it's not available. So that's key thing that we can do. Another thing that is pretty common is this. So if you have a process that requires to be close to the shipping area, so you want to keep the production close to that area, and so on. So here we have multiple things. So the idea for this diagram is that you collect all this information, and then using that information, you can create the groups as illustrated here. So in this case, someone gathered all this information, and then after the analysis, they came up with 5 different groups, and then they were able to classify the ideas into those groups using the information gathered. The next diagram is called the Interrelationship Diagram, and this one is used to map the logical links among related items to identify which items impact others the most. So as we mentioned earlier, here we have looking at the forming the product families and how would that impact others. So this arrow is identifying the formation of product families, how this affect assigning families to manufacturing cells. And then if you're assigning families to specific manufacturing cells, this has an impact on assigning the raw materials to their point of use, and also has an impact on keeping the receiving and shipping close to the production. A tree diagram, this is the third, is used to map and in increasing detail the actions that need to be accomplished in order to achieve a general objective. So this tree diagram is for the formation of product families, as we discussed in the last 2 slides. So what are the actions that needs to happen in order for us to achieve this product family formation? So in this case, we have 4 actions, 4 general actions. First is to component similarity, so finding the products that are similar that can be grouped in a particular family. Identify the machines that are used for each family. Also identify the demand per product. This will be important in terms of assigning priorities to which families are going to be produced more often, for instance, or or which ones will be produced first, and identifying the machine capabilities. So if we have a larger demand and we have a product that is selling the most, do we have enough stations and machines that can help us produce those products? And then as you move towards your right, you'll see that those 4 key actions can be split into smaller actions. So those are listed here at the right of the figure. So the usage of the product, unique parts per product, identifying common products. That's what you want to do by finding these families, because you know that when you go to production, then you can produce these multiple products that are part of the same family without having to perform too many setups into your production line. The machines that are used, so you can set up your station or your department for producing such families. This one I already explained, so this can help you identify the machines, or actually the products that are going to be produced the most, and also the ones that will have priority and the capabilities of the machines. The next one is called the matrix diagram, which organizes information such as characteristics, functions, and tasks into sets of items to be compared. So in this example, we have a matrix diagram for team participation. And then here we have 3 teams. And we have people or employees have their names here. And then we have a legend here that identifies what this means. Leader, C is for team coordinator, and P is team participant. So the idea here is like, if you are going to assign these people to this group of people or to these teams, you want to identify who's going to be the team leader, who's going to be the coordinator, and who's going to be a participant. And you want to make sure that you have a balance between each team. So for example, here, for the parts usage team, we have these 4 people participating, in which Lou is a lead, is the leader. And then for the machine use and captain, Joe becomes the leader. Joe was also a participant in the previous team. And then for the demand forecasting, you have this other group, in which you have Jack also a participant in the first 2 groups. Demand forecasting, then you have the other 3, Lou, Linda, and Daisy, which is the leader. So you're basically, the idea with this diagram is to organize the information, and then you can have a better idea of how you're using your resources. The contingency diagram maps conceivable events and contingencies that might occur during implementation. This is particularly useful when the project being planned consists of unfamiliar tasks. So you basically are stating events that can be affecting your final goal, and you list those events, and then you plan on how to address those events in the case that they happen. So here I have a very simple example, like for example, if you have a class at 8 o'clock in the morning, you don't want to be late. So if you plan for, or if you start listing conceivable events that can put you in a situation in which you might be late, then you can list those, and you can plan for strategies that will try to minimize the impact of that. So if you have ignore alarm, let's say you have a couple of alarms set up instead of just one, get close dirty So if you have an extra set of clothes ready, or if your car is low in gas, then you can plan for, I don't know, going to the gas station the night before. The next diagram is the activity network diagram. In this one, the activity network diagram is used to develop work schedule for facilities design efforts. This diagram is synonymous with the critical path method. So this is the critical path method is discussed in other courses. So here we see another use for this diagram. In this example, we have the activity network diagram example for a production line expansion facility design. So the idea of the activity network diagram is to compute how long is it going to take you to complete that implementation in this case. Like, so from start to finish, you have here that this process is going to take you 21 time units. And the way you go about it is that you plan for the start of the process. So let's say you have a process here, you have another processes here happening in parallel, and then at some point all those processes that are parallel are coming together, and then you have another process here. So you want to know what is the earliest time that you can start these, for example, these 3 tasks. And you also want to know how long is it going to take you to complete each one of these tasks, because out of those 3, the one that is finishing late or latest, or the last one finishing, is the one that is going to dictate when this one is going to start. So using all that information, then you can compute what will be the maximum time that it's going to take you to complete the process. Prioritization matrix is used, like the name is self-explanatory. You start to prioritize alternatives. So in developing facilities design alternative, it's important to consider the following: layout characteristics, material handling requirements, unit load implied, storage strategies, and overall building impact. So out of the, you start generating this list in order to achieve the goal that you want to pursue. So here we have an example that illustrates this prioritization matrix. So at the top, we have total distance travel, manufacturing floor visibility, overall aesthetics of the layout, easy of adding future business, use of current material handling equipment, investment in new material handling equipment. And we have all these actions or items that can happen. And we have a set of weights typically used to compare the importance of each pair of criteria. So for all these criteria, basically what we are doing is we are creating a matrix in which we list them. We list them vertically and horizontally. And then we start comparing 2 criteria and we start assigning how those criteria compare to each other. Are they equally important? 5 if there's one that is more important than the other, and then 10 if there's a extremely more important. 1/5 if it is significantly less important, and 1 of 10 if one of the criteria is extremely less important. So you start comparing, let's say A, they are equally important because they are the same, but if you compare A to B, then A might be significantly more important than B. So that's why we are assigning 5. And the same way you go for each one of the items in the list until you go through all of them, and then you start computing the row totals and the column totals. And that's gonna give you a grand total. You can also compute the percentage of the row totals when compared to this value. And then using that information, you can establish, like from these totals, which of the criteria has more relevance, and then you can start prioritizing for that one. Like in this case, it looks like a K has a very high value. So, and then this one 59. So we can start by looking at I, impact on WIP levels. And so on. So here's the last figure. This is the logical application sequence of the 7 management and planning tools that we just discussed. So we can start with these two, Affinity Diagram and Interrelationship Diagram, and then move to the 3 diagram. And from here, we can start with the matrix diagram and also the prioritization matrix. And if this is matrix diagram is known, then we can move to the activity network diagram. If it is unknown, then the process decision program chart. Okay, so that concludes this first lecture in which we discuss product design, process design, schedule design, and facilities design.